rotations. Right? So 2 pi r n. I don't feel like that's. I never set a timer. How far am I? Okay, well, I'm going to assume that you picked up the next video, and we're just going to continue on. I apologize for not setting a timer. Okay, well, okay, I've set a timer for this one. See if I can get to a stopping place. Okay, so, just to summarize here, previous slide we said that electrical work is the integral of electrical power with respect to time, and that's equal to the integral of voltage and current with respect to time. And we've said that shaft work is equal to, if I'm assuming that the force is constant here, and if I assume the force is constant, I plug all this in, so it's going to be force times distance. We mash all that together mathematically. And this is going to be the torque times 2 pi times n. Right? And what you'll find is that the shaft power, the power output of the shaft, I'm going to rearrange this just a little bit. It's going to be 2 pi times the torque times a quantity we'll call n dot. Right, so that's where, of course, n is equal to the number of rotations. N dot is equal to the rate of rotations. Now here's the good news. Most of the time, if I'm dealing with a shaft, a work done by a rotating shaft, most of the time it's going to be a quantity that's either given to me or I'm trying to solve for it. But in the event that you do happen to have the torque and the number of rotations, it's not hard at all to try to compute that quantity. Okay? All right. And again, the idea there is, I'm not expecting you to memorize that, just know if I see some random type of work that I'm not sure how to compute, remember that we talked about that in Chapter 2. Go refer to your notes from Chapter 2. Let's talk about spring work, right? So work done by a spring. So the force is variable for a spring. It's equal to a spring constant, or the Hooke's law constant, the stiffness of the spring, if you will, and the change in length for that spring. So the work, which again is the integral of force with respect to distance, well, here I've got a variable force, so I need to actually integrate this. This ends up simplifying down to that spring constant K divided by 2 times quantity S2 squared minus S1 squared. So if I need to know how much energy is stored in a spring or how much energy the spring releases, I need to know the change in the length of the spring in order to be able to do that. And you'll have to kind of analyze, is that energy being put into the spring or is the energy being released from the spring? And that'll help you determine whether that's work going into the spring or work going out of the spring. Okay. What else we got here? Yeah, let's talk about efficiencies. So this is lecture 3 and 4. This appears to be page number 3. Let's talk about efficiency. So efficiency is a concept that, one thing I don't necessarily care about this text is I wish it talked more about efficiency, and I wish it talked a little bit differently about efficiency, but it's okay. Right? So efficiency, very important concept for engineers. the efficiency, which we'll use the Greek symbol eta to represent that your text loves this idea of output over input. Now, I might suggest to you that that works a lot of times. If I've got a device that the goal of that device is to provide an output, this expression works very well. But if the goal of the device is to, you're putting an input into it, and you're really trying to maximize or minimize the input, that expression there may not work. What I might suggest to you is think about it. Another way to think about it is the expected smaller quantity divided by the expected larger quantity. Now, the rookie mistake there is to just say, oh, well, this is the small number, put that on top, and this is the big number, put that on bottom. You're assuming that you've calculated those correctly, which, if you're like me, you're probably going to mess up at least once or twice somewhere. Don't just simply go by which value is larger or smaller and put that on top or bottom. You have to think about, what is the purpose of this device? Do I expect this device to consume more input than it is putting out output? Almost always, yes, that's going to be the case. But it does depend on what you're calling your output and what you're calling your input. A true efficiency is always, always, always unitless. Meaning you've got the same units on top and bottom. Always. A true efficiency is always between 0 and 1. Smaller quantity on top, larger quantity on bottom. Always. And if it's not, double check your units. If your units are the same top and bottom and you're still getting a value greater than 1, double check to make sure you've got the right ratio. Don't just magically flip it and expect that's the right answer. Think about, what is the purpose of this device? What is it that we want? Sometimes, I remember a lot of times hearing this is what you want divided by what you need. Right? What is needed? What do you want divided by what is needed to get it? That's kind of another way to think about it. But again, important. It's got to be unitless, and it's got to be between 0 and 1. Okay. So various ways to think about efficiencies. I think we've got an example here in just a little bit. I don't know why this is displaying weird. The total efficiency is the product of all efficiencies within a system. So for example, if I've got just an electric generator, this is a gas-powered electric generator we might use to back up if we lost power in our home, or maybe if we go camping, glamping if you will, glamorous camping, where you take a little device to generate electricity for you. If you take a gas-powered electrical generator, it looks something like this, to where you've got some kind of a gasoline engine that generates a shaft output, and then that shaft output then turns over an electrical generator. And so the total efficiency for the entire system is going to be the product of the efficiency of the engine and the generator multiplied together. So what happens is that the efficiency of the entire system for gas-powered generator, so the overall efficiency of a gas-powered generator, well, as I said, it's going to be the efficiency of the engine. That's one component, multiplied by the efficiency of the generator. So you've got an engine converting gasoline into a rotating shaft, the heat from the gasoline into a rotating shaft, which we'll talk about engines later in the course. And you've got a generator taking the shaft output of the engine and converting that to electricity. So this ends up being, again, output over input. So the output of the engine is going to be the work done by the shaft divided by the heat that has to go into the engine from burning the fuel. And then the work done by the generator is going to be what you want, the electrical work out, the electrical energy out, divided by the shaft work going in. Right, so we know this quantity is going to be less than 1. This is going to be somewhere around 40% or so, maybe. Right? And that might be optimistic. The efficiency of it, it's got a good compression ratio, 40, maybe 50% at best, probably 30%. And then the efficiency of a generator, I don't know these numbers off the top of my head. At 50% wouldn't surprise me. Maybe it's a little better than that. So about 30 times 50, 0.3 times 0.5. You're talking about 15% of this heat from the generator actually making it to electricity, which to an electricity conversion is not terrible. Solar panels, I think, are on the order of like 10%. So the difference there is if it's a solar panel, that's free energy that we don't have to pay for, and we don't have to worry about the gas emissions, but that's another story. The goal here is to understand that if I've got a system with multiple components, each one of those components is going to have an efficiency of less than 1, and the total output is going to get decreased by every component we add in the system every time we're multiplying by a value less than 1. So the total efficiency is going to decrease the more components we add. Just keep that in mind. Kind of a neat thing that occurs when we talk about efficiencies. Okay, examples. I promised you some examples. Let's work some examples here. What do we got here? This is L3 and 4, page 4. Okay, so let's work some examples. Now it strikes me that I've not worked a manometer example, and I know most of you probably turned in that homework already, and that's okay. Right? So let's look at either some kind of a pressure change within a column of fluid or manometer problem or something like that in nature. Okay, so if we look at one of those, alright, so I've got here, let's say that I've got a tank filled with water, and I've got some kind of a U-tube manometer coming off of it. Alright, so let's say I've got water, liquid water in here, and let's say I've got, from there, some unknown fluid hooked up to this on a U-shaped manometer. Right? Now both of these we'll say are open to the atmosphere. Both this surface and that surface are open to the atmosphere. And what we know is the water elevation to where this fluid meets this one, where the water meets this unknown fluid, is 5 meters. And the elevation change from here to here we'll say is 8 meters. And what we want to do is we want to find the density of the unknown fluid. Okay? So, given. So here's the thing. I've given you kind of an example solution in the syllabus. That is a Chapter 7 problem, so don't let the complexity of that scare you off. We will get there. And it's pretty late in the semester when we get into the first and second law problems. You're welcome to follow that format if that helps you. Freestyle. Do any format you like, but what I want you to understand is I'm trying to train you how to solve problems. First thing is what are you looking for? You don't have to write the big paragraph from the text. You don't have to write that verbatim. If that helps you, by all means do. I don't expect you to. But do write somewhere. What is it that you're looking for? And if there's any givens here, right? So we know that I've got two surfaces open to the atmosphere. So I'm going to say this is surface 1, and we'll say this is surface 2. And we know that P1 is equal to 1 atmosphere. That's given. The water is open to the atmosphere, and the manometer is also open to the atmosphere. Okay? We're given some elevations here, right? We could write that down. I've got 5 meters and 8 meters. Not really sure what to call that yet. Okay? I know I've got water over here on one side, and I've got an unknown fluid on the other. Now, they didn't give me the density of the water, but I think I'm going to have to make an assumption. Well, let's set that up, right? So, where do we go from here? Well, I'm trying to find the unknown density. Well, if I could take a sample of this, I can measure it and figure that out. We're going to have to pick up from there. All right, I'll see you guys in a second.